Welcome to the next video. I'm going to change just a little bit from the syllabus. According to the syllabus, this week we'll have one video on sampling, and then next week you would have one video on surveys and constructing survey questions. I'm actually going to post both videos this week. That will give you information that you need, not only for test 2, but also as you're working on your research project. So this video we're looking at sampling. Now, I know some of you have already had your statistics classes, so you've heard a little bit about sampling, but we're going to be looking at sampling in this case from designing a research project. So it's going to be a little bit different, even though there will be a good bit of overlap. First, let's begin. I want you to open the PowerPoint that is posted online, and let's just go through this. I'd like you to try to keep up with me because there are some graphics that we're going to need in the PowerPoint. Now, let's begin by looking at where we have been so we can put this in some context. This second section of the book, we're looking at how to plan a research project. And so far, we've covered several aspects of research design, including the purpose of research, the distinction between idiographic and nomothetic research. If you're not sure what those differences are, please take a moment and think about that. We've talked about what is required to show cause and two specific types of cause, necessary and sufficient cause. Then we talked about units of analysis. We talked about time and its impact on research. We talked about the basic steps in planning a research project. And we went through the differences between research topics and research questions and how to move from a research topic into a research question. And remember, a good paper begins not with a topic, but with a question. We also, in this section of the book, as I said, we're concentrating on how to plan a research project. And so we've talked about some of the tasks that we have to complete. We began with conceptualization, operationalization, and measurement. In that, we talked about what concepts were in this process of conceptualization. We talked about social construction. We talked about the distinction between indicators and dimensions and their use in trying to measure things that are abstract or intangible. We talked about operationalization, the process through which we actually make something measurable, the different levels of measurement, things like nominal, right? If you're not sure what those different levels of measurement are, please take a few moments, go back through your notes, and remember, we listed 4 of them, 3 for practical use. And we looked at some criteria for measurement, some different ways that we can evaluate just how good our measurements are. The 2 key criteria are reliability and validity. Reliability being the chances that we would get pretty much the same answer if we did the whole thing again. And validity meaning that we are actually measuring what we say we are trying to measure. So far, we've also talked about indices, scales, and typologies, something that might be very useful in your survey construction. We talked about the difference between an index and a scale, how to construct an index, different types of scales. And finally, we talked about something that's frequently confused with an index or a scale, and that is a typology. So today we're going to be talking about one of the last things that we have to address when we're preparing a research project, and that is sampling. Now, as I've said before, and as common sense would tell you, you can't look at everyone in the population. If I wanted to find out about non-traditional college students, I can't talk to every non-traditional college student in the world. certainly. I can't talk to every non-traditional college student in the United States realistically. In fact, I probably can't even talk to every non-traditional student in San Antonio. So how can I learn about this population? How could I find out if I don't talk to everybody, right? And the way we do that is we sample. We pick a few individuals, we look at what they have to say or whatever it is we're measuring, and we assume that what we find in that sample is pretty close to what we would find in the population. That's a big assumption. And you can't just go out and start randomly picking people. You have to be much more careful. So today we're going to be looking at how we go about that process. We're going to be looking at sampling and what are called inferential statistics, which is where sampling is really important. We're going to look at what I call statistical screw-ups. Sometimes they have to do with sampling, sometimes they have to do with other things, but this addresses this distrust that many people have for statistics. And often that's based in this sampling. So we're going to look at some of the issues that are associated with statistics. We're going to be looking at two different types of sampling, non-probability sampling and probability sampling. And we're going to be talking about populations and sampling frames. Finally, we're going to be looking at some different sampling designs, including multi-stage cluster sampling as an example of just how complex sampling can get. And then at the very end, we're going to talk about some ethical issues that are associated with sampling. Because as you've known, if you should have figured out by now, ethics is really important to me when you're talking about research. So let's begin with just talking about statistics and sampling. And I know some of you are already panicked because, yes, I said the S word. I said statistics. Statistics is not frightening, though. In fact, you use statistics all the time. You use them without thinking about it, and you probably don't use them real well. But you do use them all the time. All of us do. In fact, our brains are kind of wired that way. It's how we navigate the world. In the end, though, there are two basic types of statistics. And you should really think of these as two different levels. There's a basic level and then a more complex level that's built on top of that one. And so anytime you see statistics reported, you're definitely going to see statistics from that basic level. And you'll probably also see statistics from that upper level. You really have to have both to get a complete picture of what's going on. The basic level is called descriptive statistics. And these are statistics that do exactly what it sounds like. They describe. So if I had a group of 100 people and I wanted to describe those 100 people, right? What if I could push them all into one person who was kind of like what all of them together were? That one person would be what we would call the average, right? That's the word we use, average. When we say average, what we mean is this would be the central tendency. If we took all of those heights and put them in order, or if we averaged all those heights, this would be the one kind of in the middle, right? Average. That's what we mean when we say average. In fact, there's three different types of what we in common everyday use, everyday epistemology, mean when we say average. The first is mean. Mean is the average that you learned to calculate when you were in grade school. It's the arithmetic mean. In other words, you take the measure, if I was wanting to get height for my 100 people, I would add up all the heights for all the different people, and then I would divide it by the number of people, right? Just like your GPA. That's called the mean, the arithmetic average. The second way that we can think of average is what we call median. Median means if you lined up all of those 100 people in order by height, so that the shortest person is at one end. I'm short, so I'm going to put the short people in front, okay? Put them all in order. Shortest people in front, tallest people in back, right? The one in the very middle would be the median. Mode is the height that you find most often. So let's say that you had 100 people, and out of those 100 people, 20 of them were 5'6", right? And you had other heights that had more than one person, but none of them had 5'6". Then your mode would be 5'6". Now, when we have a normal distribution, and I know you all have heard that. If you don't know what that is, just wait a few minutes. We're going to get to that. If you have a normal distribution, the mean, the median, and the mode are all the same, right? Sometimes they're not. Sometimes mean and median and mode are a little bit different. But theoretically, we kind of assume that they're all pretty close to the same thing. But if there are differences, you have to pay attention to that, because the qualities of these can be very different. Think about this. If you have 10 people and you're wanting to look at average income, right? And one of the people is unemployed, so his income is 0. And all of the other people make $10,000. That one person who's unemployed is going to make the average less than 10,000, even though that's what everyone else gets, right? Sometimes that can make a big difference. The average household income of the United States changes by a pretty sizable amount, depending on whether or not you include Bill Gates. He makes a lot of money. In comparison, mean is really not affected in the same way. I mean, median is not affected the same way. So if you have those same 10 people and one is unemployed and the other 9 make $10,000, the value in the middle is going to be $10,000. And in many cases, people think that that is a more accurate measure. The better way to describe it is to say this: the mean is easily influenced by outliers, cases that are substantially different from all of the others, like that one unemployed person sitting there with the other people who make $10,000, right? Median is much less affected by outliers, right? Mode, well, outliers don't have much to do with mode. Mode is just which one happens most often, right? So they all operate differently, and they mean different things, and we have to remember that they mean different things. We also have to remember that if they are not very similar, then we have what we call skew. In other words, there's a lot more cases at one end of the spectrum than at the other end of the spectrum. So in addition to these three, mean, median, and mode, and these are the big three descriptive statistics, but you cannot look only at those three. You have to include a third one that can be very complicated. But basically what you're trying to say here is how spread out the different values are, how similar they all are, or how different they all are. In other words, the amount of variation. And that's actually one of the measures. It's called variance. Now, variance is not the simplest way to measure just how spread out these differences are, but it's not the most useful way either. The most useful way, and the way that you'll see reported most often, is called standard deviation. And the way variance and standard deviation work is not difficult to understand if you just think about this for a minute. And we begin with even a third measure of this variation, and that is called range. So let's go back to the idea that we have 10 people with different incomes, right? One with zero and the other 9 making $10,000. In that case, we have very little variation, right? 9 of our 10 make exactly the same amount. We could have even less variance if the first person made, say, $9,500. Or we could have a lot of variance. We could have the one with zero and Bill Gates, right? So the first way to assess how much variation there is just to look at how close or how far apart the highest and the lowest value are. And it's very simple. You take the highest value and you subtract the lowest value. So in this case, 10,000 minus 0, $10,000. That's how much range, and that's the word that's used to describe it, the range between the two. Now, range tells you nothing about where on the scale those occur. So if you had the lowest income person being $100 billion and the very highest being $10,000, your range is 10,000. It's exactly the same as the 0 to 10,000. It tells you nothing about where on the scale things are. It tells you simply how close they are or how spread out they are, right? Now, variance gives us a little bit more information. And I'm not going to take you through the math now. If you want to, you can go on the internet, Google variance statistics, and you'll get it. It's not difficult. Variance is a measure, though, that is most frequently transformed, and it's very easy to do. You can look this up on Google too. Very easy to transform the variance into the standard deviation, which is usually the measurement is used. But in both of these cases, the basic theory is this. If we take like an average trend line and we figure out how far from that average trend line to each individual value each case is, and then we add them up, we get some idea of how spread out things are. The problem with that is that mathematically, when you do that, you always end up with 0. And of course, things do not have 0 variance, but it's just kind of a freaky math thing that happens when we do this. So what we have to do is actually square those distances and then add up the squares, which gives us the variance. It's very easy then to calculate that, to do a little bit of math, and change that variance into something called standard deviation. And standard deviation gives us something important. Standard deviation puts that variance on a scale so that we can compare one thing against another. It's kind of like converting that distance between the average and each score into inches or pounds. It standardizes it. So each one of them are using the same kind of units, and we can compare them. Like I said, this is not a statistics class, and I'm not going to make it a statistics class. But I want you to understand that one thing about standard deviation. It allows us to describe how close together or how spread out our cases are using a standardized unit of measurement so that we can compare them. That allows us to know whether one sample is kind of like another sample or if it's fundamentally different. Okay? So these four things, mean, median, mode, and some measurement of variance, usually standard deviation, allow us to describe any kind of sample or any kind of data set. It doesn't give us details about each case, and it doesn't give us a great deal of detailed information, but it does give us an overall description of that particular set of cases. That's why these are called descriptive statistics. The second kind of statistics is called inferential. Inferential means that from these statistics we can make inferences, we can infer, we can make guesses, we can make assumptions, we can make predictions. And that's what makes them really, really useful. Now we're not describing, we can predict. That allows us to use these tools. Okay? Now, inferential statistics are heavily, heavily reliant on samples. Okay? So if you're not there yet, I want you to go to slide 9 in the PowerPoint presentation. This slide illustrates what inferential statistics are and why sampling is so important. So let's go back to the example I had earlier. Let's say I wanted to find out about non-traditional students. Let's say I wanted to find out about non-traditional students in San Antonio, right? I'm not going to be able to talk to all of them. I want to know about all of them, but I can't talk to all of them. So what I can do is, using the proper methodology, I make what's called a random selection of cases. I pick a representative sample. That means I have a sample that is similar enough to the population meaning all of the non-traditional students in San Antonio, the sample meaning just a few people who belong to that group, belong to that population. I pick a sample that is similar enough to the population that I can assume that what I find in the sample is going to be pretty close to what I find in the population, right? So then from that sample, I can ask them the questions, or I can measure their height, or whatever it is that I'm measuring. I can collect that data from the sample. That's what's happening on the right-hand side of the slide, slide number 9. And from that sample, I might get what is called a statistic, which means I have a measurement of the sample. That's what the word statistic means, right? In this case, if you look in the bottom right-hand corner, I have what's called X bar. That's the way in statistics we write the mean, that arithmetic average. We add up all of them and you divide by the numbers. So if I was getting the average height of non-traditional students in San Antonio, I started with the population. all of the non-traditional students in San Antonio. I have my sample. That's just a few who are representative of the population. I add up all their heights. I divide by the number of people in my sample, and I get the X-bar, the sample mean. I can now infer or assume that the average height of the population is going to be pretty close to the average height of the sample. So now my mu, that's this funny little Greek letter in the bottom left-hand corner, the population mean, is pretty close to the X-bar, or the sample mean. That's what we're doing in inferential statistics. We want to learn about a population. We identify the population. From that, we go through the proper processes and identify a sample that's representative. We measure the sample, come up with sample statistics, and from those infer what the same values would be for the population. Okay, that's inferential statistics. So now that you understand that, let's take just a moment, let your mind kind of relax for a second, and we're going to talk about some of the ways that sometimes statistics are misused or mistakes that we have made in learning to use statistics. Now, these are important because as you learn to do research, you don't only have a responsibility to complete your research properly, but you also have a responsibility to be a good consumer of research. In other words, you have a responsibility to look at the research other people have done and evaluate that research to identify its strengths or its weaknesses, right? So one of the most famous cases of ways that we have grown and fallen down a little bit. It involved presidential elections. So two different people were supposed to be president, but actually weren't. The first was Alf Landon, and all of the polls said that Alf Landon was going to win. No question about it. Alf Landon was going to win, but he didn't. Instead, FDR won. Now, why did that happen? They had done their research. The problem was the way they did the survey was by telephoning people. And this was at a time when telephones were pretty new and the country was going through the Great Depression. Not everybody had telephones. And in fact, there was a substantial difference between the people who did have phones and the people who did not. And the substantial difference was money. And believe it or not, whether or not you have money affects who you're going to vote for. So people with a lot of money were voting for Alf Landon. And when they were the ones who were called, it looked like Alf Landon was going to win. But there were a lot more people who didn't have money and therefore were not included in the survey. And so when election day came, Alf Landon did not end up in the White House. FDR did. Now, statistics was a very new science at that point. And this sent everyone in statistics back to the drawing board. There had to be a better way to do this. This is when we realized that samples really did have to be representative. They had to kind of look like the population. And the way they decided to address this was through quota systems. So that later, when Truman was running against Thomas E. Dewey, a great new statistical methodology was rolled out. And what they did was look at the last census. And they kind of came up with different categories, different values. This many people are this age, this many are men, this many are women, this many work in this industry, this many live in the country, and this many live in the city, and this many have a high school education, and they put them all together and mixed them all up. So they knew that they had to have, 14 people who were female black retirees, right? All these little boxes, all these little numbers, so that the sample kind of matched what you saw in the population. And according to that one, Thomas E. Dewey was going to be the president. In fact, there's photographs, all kinds of photographs of Truman holding up a newspaper saying that he had lost the election, but he didn't lose it. If they'd gone to that much trouble to make the sample match the population, how do you explain that that didn't happen? Why were the statistics so wrong? Well, they were so wrong because we only do the census every 10 years. And in the time between when that census was completed and when the presidential election was held, there was a major shift. People were moving from the country into the cities. And so now those samples that they had tried so hard to match were no longer what the population was. And once again, certain groups were oversampled and other groups were not sampled enough. And so even though they had tried very diligently to make the sample representative of the population, they ended up with something that was not. So this is one of the big challenges that we have. We have to ensure that the sample and the population are similar. But problems with statistics don't stop there. So look at some of these, and these are very current kinds of journalism reports and other studies that I pulled off the internet that will show you some of the other problems with statistics, things that still go on. Now, people who study statistics and mathematics tend to collect these. And so if you don't have anything else to do and you're feeling really geeky, go out and look some of these up. Some of them are kind of fun. Okay, the first problem that we have with sampling is called self-selection bias. This means that maybe there's just something about the study that you're doing, or where you're publicizing your study, or what your topic is, that's going to entice some people to participate and other people not to. And as a result, you get a sample that's not at all like the population as a whole. Not because you've done anything wrong necessarily, but just because some people would want to participate in that research and some people wouldn't. And here's a great example of it on slide 13. This is the Esquire Survey of Drinking. Now, according to it, 58% of Americans have college degrees, and 26%, 1 out of 4, have a postgraduate degree. I don't even think 1 out of 4 people walking the hallway of any university have postgraduate degrees, right? This is not at all what we find in America. So how did they end up with this? Well, it's Esquire. There aren't a lot of people who read Esquire, and people who do read Esquire tend to be people who are highly educated, right? So another one is having a sample that's not big enough. We call this an insufficient sample size. So on slide 14, this is an ad I found about skincare. This was a new skincare product. And you can read the fine print if you want to, but the long and short of it is they're telling us about how remarkable this discovery was and about all of the statistics from their research. And if you read it very carefully, their research included a whole 30 people. 30 people who are paid by them. I don't think that's enough people, right, to know about the safety and effectiveness of a cosmetic. The sample size is too small. Can you represent all of the world by looking at 30 people? On slide 15, you'll see another problem that comes up not so much in conducting statistics, but in reporting them. And a lot of times you see this in journalistic products, in magazines in particular. And what it is called meaningless proportions. You're giving percentages or rates that really don't mean anything, but they make really good copy. For example, 28 is supposed to be the percent increase of men who are out in the sun, like playing golf, who have contracted skin cancer. Now, 28% increase, that sounds really, really scary, except that there's about a half a case of this for every 1,000 men. Half a case. 1 in every 2,000 people. So in that case, a 28% increase would take us from about 1 in 2,000 people to about 2 in 3,000 people. That's not so much of an increase when you look at it that way, right? So this is a meaningless proportion. If you go to number 16, this is another problem that's really not a problem with the numbers in any way. It's not a problem with the sampling. It's not a problem with how the research is conducted. It's another problem with the way the research is reported. And this one occurs, once again, a lot in journalistic products. I find this one a whole lot in USA Today. And this is when they use graphics to present percentages or rates. The problem with using graphics is that if one is this big, I don't know where you can see it, if one is this big and the second one is this big, and it looks like one is half as big as the other. When you add another dimension, you don't just double the size, you quadruple the size. So on slide 16, the 2 bars in the middle actually show a difference between 100% and 44%. But the 2 circles are what are reported quite often. And the area between the little circle and the big circle, there's much more area covered in that bigger circle. So it makes it look like there's a much bigger increase or decrease. Because people don't read the text. They look at the pictures. Another place where there's this kind of problem is on slide 17. Now, I don't know how you have your PowerPoint set up, but if you have it set up so that it's all 3 of these that show up at one time, you're going to lose some of the effect. There's better drama if you have it set up so that on 17, first you just get 1 picture, and then 2 pictures, and then 3 pictures. Okay, if you don't, we begin with the picture in the upper left-hand corner. And what this is the stock market. This is the stock market from one day a few months ago. And it's actually the stock market between 10 a.m. and 4 p.m. on this one day. Looking at that picture, it looks like stock has just plummeted. Oh my God, it's a stock market crash, right? But if you look at the picture below it, the one on the left-hand bottom, that is the same stock market, only now it's not in terms of one day, it's the stock market for 1 year on that day. For 1 year on the same day. In other words, that very tiny, tiny little slice on the right-hand side includes all of that stuff in the top, right? Now looking at that one, stock market doesn't look like it's doing that bad. it's kind of been going up. I mean, it looks like we had a really bad time not long ago, but it doesn't look too bad, right? Certainly doesn't look like the first slide. It does not look like you just had a stock market crash. Now look at the slide on the right. Once again, from the same day. And what you have is the history of the stock market since its beginning. Well, that big drop that you saw in the first slide doesn't even show up. It doesn't even register. And it doesn't look like we are having a hard recession. It looks like we dipped a little bit. But overall, we're doing great, right? So the amount of data that you present in a graphic can radically change the message that you send, right? These axes. Now, I could have made these even worse. I left these with the same horizontal and vertical ratio that they originally had. But what if I had taken that first one and stretched it vertically? I had made it twice as tall as it is, but left the width just like it is. Wow. Now that depression is really, really bad, right? So you got to be careful with these graphics. And as a consumer, as a researcher, you have to be aware of this because we count on you. The people who trust you to do the research also trust you to catch these kinds of things. Okay? So when we start looking at statistics, the moral of the story is that the numbers don't lie, but the accuracy and the honesty of any kind of research, especially statistical research, can be compromised by poor design, poor research design. Maybe your sample isn't the sample it should be. Maybe you need a bigger sample. It can be compromised by irresponsible reporting. If your graphic does not visually say what the facts really are, it's the same as lying, right? And finally, it's compromised by a public that doesn't understand statistics. And that makes them easy to fool because they trust people that maybe they shouldn't. As I said, this becomes your responsibility. Now that you've had this research class, and when you leave, you will be an experienced researcher. This is now your responsibility. So, now we're going to go into non-probability sampling, one of two basic types of sampling. Now, as I said, what we would hope to do is have a sample that's really similar to the population, right? Sometimes, though, we aren't really sure about that population. Let's say I wanted to do research on illegal immigrants in San Antonio. I probably get a little bit of entrance, but there's going to be a lot of people who are really hesitant to talk to me, right? There's no real way I can thoroughly identify that population. So I can't really do an accurate sampling because I don't know what the population looks like at all. In those cases, I have to go not so much with a representative sample, but with whatever sample I can find. And I just have to acknowledge that this is going to be a weakness of my research, but it's the best I can do. We call this non-probability sampling. Now, there are 5 basic types of non-probability sampling, and in each one of these, we're going to think about me doing research on undocumented workers in San Antonio. One is just what's called a convenience sample, or a reliance on available subjects. So let's say that, I found a crew of people working and just somehow knew that, oh yeah, the people who had that job didn't have green cards. So I walked over, and that's who I talked to. That's a convenience sample. The most frequently used convenience sample is college students, because most researchers are professors and they have students there. And if you want people to take your survey, all you have to do is offer extra credit. And that's what happens all the time, right? It's not that those students really are like the rest of the population, but sometimes they're the best you can get. A second way we could do this is purposive or judgmental sampling. So perhaps, once again, I'm looking at undocumented workers. Perhaps I could find a place where I thought people might be most likely to go if they were undocumented workers. Let's say there was, I don't know, there's some sort of class that's teaching English, or perhaps there's some sort of public meeting for people who want to apply for green cards, right? And I just kind of show up there, right? Now that sampling, I cannot assume that that sampling is representative. Number one, I can't assume that everyone who's undocumented wants a green card, right? But I can know that that's where I could maybe meet some people. And so that's maybe the best I can do. A third way is called snowball sampling. Snowball would be, maybe I know a couple of people. So I give them some business cards and I talk to them about what I'm doing. And I say, hey, if you have any friends, would you please have them call me? And a few of their friends do call. And so I talk to them and I tell them thank you, and I give them some business cards and I say, would you please have your friends call me? And pretty soon it's spreading out. And it's word of mouth. Once again, not representative at all. Sometimes it's the best you can do. Another way would be just a quota sampling. Maybe I have some information that, this percentage of workers are in one category and this percentage of workers are in another category. And I'm just looking for people who can fill those categories. Of course, we saw in the beginning here when we talked about Dewey that that's not a reliable way. But sometimes it's the best we can do. Finally, we can just use informants. There's a marvelous study. I know some of you have an interest in criminal justice, perhaps in gangs. There's a wonderful study by Padillo. Padillo was a grad student in Chicago, and he ended up without a place to live one night and found a kind of a cheap-looking apartment complex with the door open. Ended up trying to sleep in on the landing of the staircase. As it turned out, it was a building that had some gang connections. And over the course of time, he made friends with some of the gang members. Began just kind of hanging out on this landing in this apartment building. And did a wonderful study. Found out all kinds of information about this particular gang that people generalize. Now, if you're using logic, that's a hasty generalization because you can't assume that one group is like all of the other groups. But sometimes it's the best you can do. So that, once again, we'd rely on non-probability sampling. In contrast, probability sampling attempts to ensure that the sample really is going to be pretty much like the population. It is representative, which means the characteristics of the sample are roughly equivalent to the characteristics of the population. Now, they don't have to be representative in every way, but we do want them to be representative in those factors that we think are most relevant. If we think that race, age, and gender make big differences in voting populations, for example, then we need to use a sample that is representative on those three aspects, right? We also need to use what is called randomness. Randomness means that every member of the population has an equal chance of being included in the sample, right? Does not mean some of the other explanations that I've had students give. Sometimes there can be a formula involved, but it's not the formula that makes it random. What makes a sample random, once again, is that every member of the population had an equal chance of being included in the sample. Okay? So when we start talking about this situation in which every member of the population has an equivalent chance of being included in the sample, we suddenly have moved over into the land of probability. Now, probability can be thought of as luck, right? It's the likelihood that something is just happening by chance, just happening naturally, without any interference, okay? So think about this like flipping a coin. Flipping a coin is like the basic example of probability. If you're flipping a coin, what is the probability that you're going to get heads if you flip it one time? Of course, 50%, right? 50% heads, 50% tails. Because it's going to be one or the other. It can't be anything else, right? Just as likely to get heads as you are to get tails. Probability, luck. Now let's extend that just a little bit. Let's say that instead of flipping that coin one time, you're going to flip that coin 10 times. Now, you could be the one strange person who flipped it 10 times and got all heads. Or you could be the one strange person who flipped it 10 times and got all tails. But what's most likely is you're going to be the average person and you're going to flip it 10 times and get 5 heads and 5 tails. Or something close to 5 heads and 5 tails, right? So let's look at what that would look like in a chart. So I want you to go to slide 25. And what you see here is the probability, the likelihood of flipping all heads or all tails. Those just little bitty histogram bars on the left and on the right. Or the possibility of getting 5 heads and 5 tails. That's that tall bar in the middle. This is 25%, right? So 25% of the time you're actually going to get 5 heads and 5 tails, right? A little bit less likely you're going to get 4 heads and 6 tails or 6 heads and 4 tails. A little less likely than that, you're going to get 3 and 7. Less likely than that, 2 and 6, right? Then 1 and 9, and then almost no chance of 10 of either one. That's your probability distribution. But what if instead of doing 10, you flip it 20 times? Look at what happens now. We have the same shape. It's a little less likely to get 10 and 10. You know, down here, about 17 or 18% chance, right? 17.5. And almost no chance that you're going to get 20 heads or 20 tails. But look, the overall shape of slide 25 and slide 26 is really similar, isn't it? The two sides are equal. The two sides are like mirror images of one another, right? And they go up in the middle, and they go down on each side. So you have this increasing probability and then a decreasing probability, right? If instead of just flipping those 20 times, we could flip that coin infinitely many times, it stops looking like bars at all. And what it looks like is just one curve, like in slide 27. And this, ladies and gentlemen, is the normal curve, right? The normal curve has several characteristics. The two sides are symmetric, meaning that they look just like one another. They're mirror image. It's asymptotic, which means that the curve never actually touches the axis. And it's hard to see that in slide 27. Trust me, never quite touches the axis. The mean, the median, and the mode in a normal distribution are all equal to one another, and they are all equal to 0. Okay? And then we get into the question of standard deviation. Remember when we talked about standard deviation? In a normal distribution, the area of the curve, all of this space between the axis and the curve, that's called the area under the curve. The area under the curve that ranges from one standard deviation, a -1, to another standard deviation on the other side of the 0. It's a positive standard deviation. So between the -1 and the +1. This area is 68% of the area under the curve. If you look from -2 to +2, 95% of the area under the curve falls there. And 99% of the area is somewhere between 3 standard deviations above and below the mean, right? Between the -3 and the +3. The reason that's important is because in the normal curve, the amount of area that's represented under the curve is equal to the probability, okay? So the chance, if you're flipping coins, the chance that you will flip something that lies between -1 and +1, you're going to get something in this area. There's a 68% chance that that's going to happen. There's a 95% chance that you're going to get something between -2 and +2. And a 99% chance that you're going to get something between -3 and +3. Okay? Even if you don't understand all of that, roll with me for a little while, okay? That probability is how we can identify situations that stand out. Situations that are unexpected or unique, right? We call those situations that are significant. They are so rare that it's very unlikely that they happened by luck or by accident. Typically, we say that anything that has less than a 95% probability of happening is significant. It's rare. It's unexpected. So we are looking for those things that fall outside of the second standard deviation, right? Things between -3 and -2, or things between +2 and +3, or even things beyond the 3's, because remember, the curve is asymptotic. It never touches the axis, so you can be bigger than 3, okay? And I know, as I said, I know, especially if you haven't had statistics, that doesn't make a lot of sense. Just roll with me, because this is what we're looking at when we do statistical analysis. What we do is use the math and plot our findings on this normal curve. And if those findings show up outside, usually outside of the -2 or the +2, then we do our happy dance. We found something significant. Okay. Now, I'm going to go back to the idea of the number of coin flips making a difference, right? One of the reasons that makes a difference is because we got more precise. See, if you look at slide 25, you've only got 10 possibilities. The next one, you've got 20 possibilities. This one, you've got infinitely many possibilities. So precision is increased. Another way to say that is that as the number of flips increases, the accuracy increases. But each one of those flips is basically a sample, right? Or a case. The number of cases. As the number of cases in your sample increases, your accuracy also increases. A larger N, better sample, okay? But it's never going to be exact. It's never going to be perfect. No sample is going to give us a perfectly representative indication of the population. And so we have to just admit that there's always going to be a little bit of fudging. We call that sampling error, okay? And we can build that into the math, and that's what we do. We can also, though, calculate things like a confidence interval. That means that's the area where it's most likely that the population really is. Not exactly what the sample says, bigger than what the sample says. Broaden it a little bit. But we can be pretty sure that that population, that parameter, is somewhere within that confidence interval. We can also calculate a confidence level. How certain we are that that parameter falls within that confidence interval. But at no point do we say this is what it is. We can't do that. Statistics is not about precision. It's about likelihood. It's about probability. We don't promise anything. We say, this is likely. Okay? It's all about the odds. So statistics cannot tell you what's going to happen. It's not fortune telling, and it cannot tell you what is happening with 100% certainty. What it can tell you is what is most likely. And we understand this when we think of the way that statistics are used without being called statistics. Think about gambling, right? We don't think about promises. We think about odds. And the way that those casinos calculate the odds is by using statistics. Okay? So, having talked about all of that, let's also talk very briefly about sampling frames. And I'm going to rush through this a little bit. If you want to read a little bit more, you can do that. But sampling frames are basically when we have a situation where we're not even really going to try to look at the whole population. We're going to look at, this particular means of getting data, or this particular subset of the population that we're interested in. And sometimes that's just what we have to do. We might call people from the phone book, and we don't really do that anymore. But sampling frames, we're really not dealing with the whole population. We're trying to research them ultimately, but we have to begin with something a little bit less. Sampling designs, then, And there are several sampling designs, different ways to draw our sample. The first is just simple random sampling. You get a group of potential sample members, and you just use random numbers. So if I wanted to take a sample of TAMUSA students, right, I might set up some sort of random table with all of the K numbers and randomly pull those out. Pull them out of a hat, basically. There's also systemic sampling, which is actually probably the most common form of sampling. So let's say instead I'm looking at students at TAMUSA. I just get a list of all the students and I say I'm going to begin randomly at case 14, and then every 10th person after that goes into my sample. Okay. Sometimes you do that by ratio, sometimes you do that by interval, but it's all the same thing. You start randomly and then you pull every case, is the way it's usually written, case. Now, with your sampling designs, you can also get more intricate. And one way to do that is with stratified sampling, which can be extremely important in the behavioral sciences. And here's why. Let's say that you wanted to make sure, you wanted to look at racial groups. Okay, it's a place where it's used quite often. But let's say that in your sample, because there are very few Asians in San Antonio, you did a sample of 400 people and you ended up with only 2 Asians, right? That might be good or that might be bad. Maybe that is the same kind of rate that you would find in the United States. And if that's the case, yeah, you're probably okay. But it begs the question, can you really expect 2 people to represent a whole racial group? And so sometimes in stratified sampling, we say, we really don't have enough variation there. We really need to have at least 10 people. But that would mean either you have to increase all of the samples you have in every group, or maybe you could get 10 people who are Asian and kind of condense what you find there so it only carries the mathematical weight of 2 people. And that's called oversampling. It's something we do quite often, so that we end up with racial groups that are weighted to represent the proportion of the population that they actually hold. But we have enough variation within each group to make sure we really are getting all of the information that we need. We're not just relying on 1 or 2 people. And as I said, some of these sampling methods can get extremely complex. In your textbook, he talks about multi-stage cluster sampling, which is a pretty complex sampling method. Cluster sampling means that you have pre-existing subgroups. Okay? So if you wanted to look at school-age children, instead of just randomly selecting school-age children from all over the country, maybe you randomly select a sample of schools, and then within each of those schools, you randomly select some students. That's multi-stage cluster sampling. It's very effective, but there is something you have to be aware of. If you do that at 2 different levels, what you have is error introduced at 2 levels, because you have basically 2 different samples. You have a sample of schools and then a sample of individuals within the schools. So you have increased the likelihood of error. And some of these can get extremely complex. On slide 40, I have a kind of a flow chart of a stratified sampling, cluster sampling methodology that was used in one data set that I use pretty often in my research. And so as you can see, you had different high schools and then different feeder schools for those high schools, and then you had different samples pulled out of those. You got very, very complex, but very detailed information. Wonderful, wonderful data. Now, we're going to finish up with some ethics. The first and most important, and one of the messages I want you to take out of this class is there is no perfect research. No matter how hard you try, and no matter what you do, there is no perfect research, especially when you're dealing with people. There are always limitations. And it does not make you look like you don't know what you're doing if you admit those. In fact, it makes you look professional and honest. Okay? The limitations are there. And good researchers who read what you've written and see what you've done will know those limitations are there. They'll only trust you if you let them know that you know they're there. Okay? Does not mean your findings are unreliable or that they're invalid. It could be that someone would do this in a slightly different way and get almost exactly the same information. In fact, if that happens, that means your research was really good, right? It doesn't mean it's invalid. You can be measuring exactly what you say you're measuring, but not measuring it perfectly. Okay? But be precise and be honest and build on the shoulders of giants and hope that someday someone's standing on your shoulders. See you next time.